Hi everyone, thank you for joining today's talk. My name is Seung, and today I'll talk about our work, large graph convolutional network training with GPU-oriented data communication architecture. First, let's briefly talk about the graph convolutional network. The goal of GCN is to create a high-quality embedding of a target node by using a relational information. Therefore, unlike the other conventional neural networks, GCN requires the features of the neighboring entities to create the output embedding. The collection of the node features are stored as a tensor, and each node features is indexed by its node ID. Here, because the node features of the neighboring nodes are in a sparse manner, it is impossible to transfer them to the other device in a single block data transfer. The current method of transferring sparse data to GPU is to gather the sparse data into a dense data and then perform a block data transfer to the GPU. However, this gathering step is costly in a sense of memory bandwidth. In the diagram, we show the three stages of memory access required to finish this operation. First, the CPU reads scatter features from the host memory. Second, the gather features are written to the new contiguous buffer. And finally, the scatter features are read by GPU DMA engine. This means, to transfer X amount of data from GPU, we need to access the CPU memory 3 times of it in total. Under these circumstances, with an increasing number of GPUs, the total bandwidth that the CPU memory needs to sustain becomes quite significant. To overcome this memory overutilization problem, we propose a zero-copy access-based GCN acceleration with NVIDIA GPUs. In the diagram, we show the system-level node feature access operation with the zero-copy accesses. Since this zero-copy access enables GPUs to directly access the CPU memory, we only need to transfer the indices to the GPUs, and then GPUs can use those indices to directly access the targeted node features in CPU memory. The benefit of this method is that there are no more of the redundant memory accesses, and we can reduce the CPU bandwidth usage to 1/3. Yet, we still need to do some optimizations to make the zero-copy truly performant in practice. From this slide, we'll explain several zero-copy access optimization techniques that we applied to further improve the benefit of using zero-copy access for the GCN training. The first optimization is an aligned memory access over PCIe. When accessing certain node features which are not aligned to the GPU cache line, the following zero-copy accesses can be broken down to smaller PCIe requests. To overcome this issue, we implement an automatic alignment optimization which is aware of the GPU cache line size and shifts the indexing indices in a circular manner until each warp's memory requests are aligned to the GPU cache line size. In this specific example, after applying the indexing shifting, we can coalesce more number of memory accesses, and the total number of PCIe read requests dropped to 5 from 8. As we can see the results on the right side, applying the alignment fix can provide additional 10 to 15% of bandwidth improvement. The second optimization is an asynchronous operation of zero-copy access. Unlike the regular DMA-based data copies, zero-copy accesses are done by GPU kernels, and therefore they occupy the GPU cores. When the GPU cores are consumed by the zero-copy accesses, other GPU training workloads must wait until the zero-copy accesses are finished. In this slide, we show an end-side profiling result when we are training GNN with zero-copy accesses. Since the zero-copy kernel is occupying the GPU cores, the training kernels which can be executed in an asynchronous manner must wait until the entire zero-copy operations are done. In this work, we resolve the serialization problem by adopting the CUDA multiprocess service, or MPS. MPS allows the users to control the maximum GPU utilization of a certain process. With this capability, we can distribute the GPU resources between the computation kernel and the zero-copy access kernel. On the right side of the slide, we show the empirical result of using different GPU partition ratios for the zero-copy accesses. When we allocate about 2.5% of the GPU resource for the zero-copy kernel, the bandwidth is limited to about 10 GB per second, which is significantly lower than the maximum PCIe Gen 4 bandwidth. However, as we start increasing the portion of the GPU resource allocated for the zero-copy kernel, we can clearly see the zero-copy bandwidth is also increasing. In our setup, we get the best performance when the 10% of GPU resources allocated for the zero-copy kernel. Now, we want to spend a few minutes talking about the challenges of adopting our method into the existing DMA frameworks like PyTorch. PyTorch assumes the operand tensors are in a local memory of the processing unit that executes the operator. For example, a GPU kernel can only access operand tensors in its device memory. If we try to perform an addition of a CPU tensor and a GPU tensor, this will lead to an error. Therefore, directly accessing the CPU memory from the GPU is simply not possible in current implementation of PyTorch. Next, even if we somehow enable the zero copy access in PyTorch through a hacky data pointer manipulation, we'll still need to resolve the identity of the output tensor of the GPU operations. For example, the output tensor of the normal GPU operations will be a GPU tensor. However, in our case, due to the cross-device memory access capability, the identity of the output tensor becomes somewhat unclear, and it can be either located in the CPU memory or the GPU memory. In GCN training, we specifically want the output of the zero copy access to be in the GPU memory for the subsequent GPU training processes. To enable more control of the data allocations for the PyTorch programmers, we need to provide a more systematic way to support the cross-device memory access capability in PyTorch rather than a hacky way. To deal with the challenges, we introduce a new class of tensor called unified tensor. The unified tensor encapsulates the logic needed to enable the allocation of zero-copy memory region and cross-device accesses. Also, creating the independent type of tensor for the zero-copy access allows us to add capability of selectively enabling PCIe-related optimization in certain GPU kernels. To address the second challenge, we designed two affinity modes. Each unified tensor is assigned with one affinity mode, which is by default GPU-affinitive. The corresponding operators are executed by GPU, and the results are stored in GPU memory. Specifically, applying subscript operator to the GPU-affinitive unified tensor triggers the zero copy access that we want exactly. In the meantime, we also provide host affinity mode as an option to have the CPU perform the execution and keep the result as a unified tensor. There is no data movement when the affinity of unified tensor is switched. Now in this slide, we show the end-to-end GCN training performance gained by using zero copy access and our optimizations. In the left side, we compare the single epoch training time of different methods across three datasets. For this CPU-only case, we only use CPU to train the whole GCN. For the DMA-based method, we use CPU to gather the sparse features into a dense format and use DMA to transfer to the GPU. In case of zero copy, we divided into two categories where we did not and did apply the optimization we discussed. Throughout the experiment, we observed that the optimized zero copy method is faster than all other methods. For the Wikipedia dataset, since the whole dataset can be fit into the GPU memory, we also compare our method with the all-in GPU memory case. As we can observe from the comparison results, our zero copy method can completely hide the PCIe data transfer time over the training time, and therefore it can't match with the all-in GPU memory case. On the right side of the slide, we compared the zero copy method and the DMA-based method with a varying size of node features. With the small node features, the performance improvement of the zero copy method is limited to about 1.5 times, but with the larger node feature sizes, the performance improvement of the zero copy method becomes about 2.7 times. This result shows the importance of using efficient data access mechanism with the larger node feature sizes. Thank you for listening to our talk, and please let us know if you have any questions. We have also open sourced our code in the following GitHub repository, so you can directly go to the following link to get an access to the source code. Thank you.